Sorry. Our final speaker, besides the closing remarks, of course, is Bruno Coimbra. Please.
Can you hear me? Okay, so hi everyone. My name is Bruno. I work at Formulab, and today I will be presenting on behalf of Marco Mascherani, who unfortunately couldn't be here in person today. I think he's connected though. So this talk is about the federated HTCondor infrastructure that CMS has and how they monitor and manage this using several tools. So starting here, so CMS is one of the general purposes for this experience at the LHC at CERN, amounting for all the data collected and distributed and reconstructed and analyzed. It produces hundreds of petabytes a year. And to manage that, CMS leverages the WLCG, which stands for Worldwide LCG Computing Grid. And it's a collaboration around the world that basically amounts for 170 computing centers that have dedicated resources with more than 1 million CPU cores and 2 exabytes of storage. And to manage all of it, CMS relies basically on HTCondor tools. So HTCondor by itself and also FlyWMS. The quick summary of what FlyWMS does, it basically creates a virtual cluster, which we call a global pool. And the way it does that is that we have a front end that basically watches an access point. And depending on how many jobs it has in the queue here in the access point, the front end will send out requests to a factory that will therefore send out pilots to an execute point. By the way, for gliding at advance, we call these pilots glidings. And the gliding will say in queue. When it starts running, it will start another execute point here, which will be the second layer, which will talk to the central manager that will make those slots available for the access point. This system works on a pressure-based system, which basically tries to make sure it always has a number of pilots queued up, so a number of pilot jobs waiting to start. That's basically how it goes about it. So in practice, we operate this federated pool to over 70 grid sites and other non-grid resources. Besides the global pool that we just mentioned, CMS also uses the CERN pool, which is a dedicated computing cluster at CERN. These are mainly used by production jobs coming from the tier 0. We have the global pool for analysis jobs, and it also plots some of the production jobs. At Formulab, we have the HTCloud pool, which we basically use to make CMS jobs inside. We also have these volunteer pool here, which is actually a pretty cool project. Volunteers can install software on their computers to basically volunteer idle CPU time that they have on their machines to CMS. And we also have some external pool here. To give an example of the amount of the capacity that HTCondor provides to CMS, here we can see that we have at one time about over 160,000 jobs running at the same time. We can see here in 2 colors. In yellow, we have the jobs running at CERN. So basically production jobs running locally at the CERN pool. And some of the jobs are actually plugging as well to the global pool. These are all tier 0 jobs, production jobs. This other visualization here shows that some of these jobs use 16 cores, other 8 cores, 4 cores, 2 and 1 core. So we use gliding basically use partitionable blocks. And then motivated by those visualizations, something that really comes in hand here is having a good monitoring. Monitoring is important. Well, basically, to be able to manage the global pool over 70 sites, and you have a lot of resources that we have to make sure are working. It adds reliability, right? So we can detect problems and solve them as soon as possible. It helps with operations to understand what's actually going on the specific sites. And to create this monitoring, CMS leverages the CERN monitoring infrastructure. That's basically the software suite with a bunch of monitoring tools that are updated every 12 minutes. So you always have a very recent picture of what's going on the experiment grid. And for the first example here of these monitoring tools, we have the visualization for the HTCondor HTCondor job frame. So these are basically the job frame. And by monitoring the jobs, we can see there, we can use actually information that we get from HTCondor Q, from Column Q, for example, to see their states, their runtime efficiency. We can see the number of slots we have available. We can see how our schedules look and negotiated and so on. And these are basically done by querying logs for these kind of demons here every 12 minutes and then pushing data to the CERN one. These are a few examples here. So this is how we monitor the scheduling. These are basically the duty cycles of every scheduling that we have. Then we have some data for the negotiator as well, some worker nodes specifically, so machine monitoring here, and a general collector health plot. Going down one layer, because what we were seeing so far was basically the resources that we get in the virtual move layer. But it's also important to monitor the VMS itself to see how the underlying system is performing. So to do that, we actually watch the VMS components here. We have then information about so we basically have to run specific scripts that run on the factory in the ground here that will query information about the value of these three different components of the VMS system here. And then we have an aggregating system for having all the related component jobs in one place. So here, for example, this is what a front-end monitoring looks like. Here we're basically checking the number of requests that we have to the factories. It's interesting to note here that in this plot example here, we have the peak valley here. This is basically lack of pressure, which means programs are not requesting lineage to the front end. This might happen for a number of reasons, but very likely here it's just that we don't have jobs being sent to a specific schedule that these front ends are watching. And another example that we have here is these gaps that we have here for two of the factories, which likely happened because of some update issues with the factories, since we have at least one factory still with full run. Here we have the factories working as well. So these are basically the number of errors that we have for specific factories. So we monitor a number of general failures, typically if the factories put into pilots, and if they have any issues, they are going to watch that in the factory. And we can categorize them in some specific failure categories. So we have startup failures here, validation failures, or simply idle plots, idle pilots, and we plot them all here so you can have a general idea of what's going on. And these specifically useful to detect site problems or some distributed resource issue. I don't know, you can address an RX for some specific site or something like that. And this basically enables operators to take action. They see something like that here. If you want to go into the specific details of why the final jobs are failing, we have these glide Muon service here that basically aggregate the gliding logs. So whenever gliding starts out on the worker node, it will produce logs that will then be transferred to the factory. These services here basically aggregate them. So we can basically drill down on the problem and see what exactly failed for that specific light and on a specific site. In addition to all of this monitoring, CMS also implements a bunch of thresholds that basically will trigger alarms if specific plots go over specific thresholds. So we can see here, for example, if the negotiation cycle goes over this threshold here, it's going to trigger an alarm. Same thing for separated sketches, or here the number of cores ever go below, I guess, your 30K plot. It will also trigger an alarm. And this is pretty useful for operators because they can catch the problem as soon as possible, often before users even realize there is a problem, and they can come up with a solution, reducing as much as possible the downtimes. So in short, CMS relies on this large-scale federated HTCondor infrastructure, spreading over 70 grid sites. It uses monitoring to make sure everything runs reliably and efficiently. They have these very comprehensive and modular monitoring ecosystem that leverages CERN for that, enabling operators to be proactive on their support of the site, of the whole experiment, actually. And that's it. Congrats from CMS to the 40 years of Condor. And with that, yeah, that's it. So thanks, everyone.
Questions for Bruno? And we have one back here. And another one down there. Yes, race for it.
Hey, Bruno, thanks. Thanks for that talk. It's very hard to, I think, get a handle on even on just one factory. So seeing you try to wrangle a bunch of these is pretty impressive. Oh, sorry. I was saying that was it's difficult enough to keep track of one factory. So the fact that you're able to get a handle on multiple is quite impressive. I was wondering could you remind me what metrics you're pulling out of the pilot logs themselves, and is there any plans to like expand on that? Like what kind of things can you diagnose with the things that you're getting out of the pilot logs?
You mean these logs?
Right, yeah.
Yeah, so these logs are basically and Marco, if you're hearing, feel free to correct if I want to, because again, it's at the basically not fine, Marco. But the startup logs are basically as any file. It's everything that happens in the player startup. So if anything goes wrong, it's going to go either on the standard out, which is the output here. So job number, that is considered out for the output. So usually what you would look here is for everything that the job is downloading, for example, so once the client, we will download a bunch of scripts, credentials. We will then validate everything, do some health check and dependency check of the specific worker node. Finally, if everything's fine, it will start beacon. So these are the kind of information you can find here in the descendant out one. If anything goes wrong, any error, you find the descendant error file, which is a different file. Basically the same thing down there. Now, what you would look for here is basically, let's say, if in the factory plots here, you saw something going wrong. So let's see, you may see a spike of startup failures here. You may want to go into those logs and see exactly what specific error is causing the startup error. So you can then probably address one specific site issue that is happening. Let's say if CVMFS is down for whatever reason, this is going to cause startup issues, and then you can find these that are in the gliding logs.
Okay, and would this actually show up as like this is a CVMFS error here, or would that be something you'd have to go diving into the log for? Right. Would you actually be able to tell from what you're logging here that you're having specifically a CVMFS issue, or would you have to go? You just know that a site has an issue and you'd have to go.
Was only You have to go with like.
Oh. Gotcha.
Right.
So the glide-in log there, you have to wait for the glide-in to complete, right? So if the glide-in runs 3 or 4 days, you don't get anything until the 3 days is up.
No.
Oh, interesting.
I think the bigger problem is if it's being preempted or hard killed, then you don't get the logs either.
Right. Yeah.
What about now? Yeah, first somehow it turned off. Was it off during the whole presentation? Okay. Oh,
Which is on.
Okay, so once it completes,
once it completes, it
You
transfers the
get it
logs
back.
back to the factory. Yes.
and if it's hard killed by the site, sig killed, then you get nothing back, right?
80% sure you do not. Yes.
Right. Thank you, Bruno.